To do good system testing, it is essential to understand requirements, even if you don't write them yourself. There are 5 areas we will look at: what requirements are, good versus bad requirements, requirements and their implementation, as well as requirements in test cases, and what to do in practice. We will go through each of them. A requirement is a statement of what the product must, should, or may do. It captures the intent of a customer, a user, a regulator, or the business. There is an important distinction between a requirement and a specification. The requirement describes what is needed, so the problem space, while the specification describes how it is realized, the solution space. Requirements typically fall into 3 categories. First, functional requirements. They describe what the system does. Then non-functional requirements, which describe how it behaves. So the performance, reliability, safety, or security. And then third, the constraints, which come from regulations, technology choices, or the operating environment. In system test, the requirement is the upstream test basis. It is not the only one. Use cases, expert input, and regulations are also fed in, but it is the central anchor. Next, good versus bad requirements. A good requirement has 6 properties. It is atomic, meaning one requirement implies one behavior. It is unambiguous, so only one possible interpretation. It is complete, meaning that all conditions, inputs, and outputs are covered. It is testable, so a test case can prove, pass, or fail of the requirement. And it is traceable, so this means it has a unique ID and can be linked up and downstream. And it is feasible and properly prioritized. You may have seen the related abbreviations to remember the attributes like SMART, INVEST, or the IEEE shell style. They all point at the same properties. Bad requirements show up in patterns. So let's walk through the most common ones. First, if requirements are vague. So for example, the system shall be fast. This is bad and should be fixed by, for example, the response time shall be below 200 milliseconds. Then compound, like log errors, notify the user, and store events for 30 days. Fix it by splitting it into atomic requirements, so splitting them in 3 distinct requirements in this case. Then requirement is mixed with solutions. For example, use a Kalman filter to estimate the position. Focus only on the need and leave the algorithm to the design and the implementation. Then subjective. The UI shall be intuitive. Anchor this with measurable proxies, like task completion time, error rate, or something similar. Or an example for untestable requirements. The system shall never crash. This is of course desirable, but not a good requirement. So put some boundaries to it, like no unhandled exception under defined conditions over a defined period. When you're working with bad requirements, the rule is simple. Raise the gaps early. Do not silently invent the missing detail yourself. If you are forced to derive tests anyway, write down your assumptions and test each interpretation explicitly. A bad requirement always produces either bad code, bad tests, or both of them. So now looking at requirements and test cases. Test specification is the discipline of converting requirements into executable test cases. The input is the requirement. The doing is to derive the testable behavior, define the precondition, the actions, and the expected outcome. The output is the test case and a set of test cases that together cover the requirement. A one-to-many relationship is normal for requirement testing, but at least one test per requirement is mandatory. You can categorize test cases per requirement into a positive case, a negative case, boundary values, or error path. The mechanics of deriving test cases follow a clear pattern. First, identify the testable statement, a verb plus a measurable outcome. Then determine the preconditions and the inputs. List the expected outputs and observable reactions. Then pick a technique, for example, equivalence partitioning, boundary value analysis, or a decision table. The quality of requirements determines the quality of test cases. An unclear requirement produces a vague test case. An untestable requirement produces no test cases at all, and that becomes a coverage gap that is invisible until it isn't. Traceability ties that together. Every requirement should have at least one test case. And every test case should reference to a requirement. This linkage is bidirectional, and it lives in the test management tool or in the requirement management tool. That is what enables coverage checks, impact analysis, defect analysis, and compliance evidence. So what does this mean in practice? Requirement management is its own discipline with its own tools and its own roles. Testers and QA in general are not just consumers of requirements, they are also their reviewers. So looking at requirements early is one of the highest leverage activities a tester can do. Also, you have to consider that requirements evolve over time. This means versioning and impact assessments are not optional, but very crucial so that the project stays consistent through change. And testers and QA in general hold very strong leverage by getting involved at the requirement stage and not waiting until the test execution. So to summarize, requirements are the upstream basis for both implementation and tests. A good requirement is atomic, unambiguous, complete, testable, traceable, and feasible. Bad requirements, on the other hand, always produce bad code and bad tests. Testers and QA add the most value by reviewing requirements early, not by just waiting for the test execution.